solve for both. And from the x-axis equation, we solve for v relative. From the y component equation, we solve for omega. This is the angular velocity of this BD link. Then we move on to our next evaluation in the acceleration domain, because we already received all the necessary information in the velocity domain. We received the information about v relative and omega. That was all we need, right? This is all we need. Omega, v relative, there is this omega information. Alpha is the one that we are looking for. So we can again write out two equations about the acceleration of this A point. We can write out an equation based on the rigid body motion. There is these 2 points on the rigid body, A point and B point, and they're related with respect to this A relative to B, acceleration of A relative to B, and it has two components, one component in the tangential direction, the other component is in the normal direction, if you remember. These are the parts of the acceleration, and alpha is what we're interested in. Omega is something we already found. BA vector is something already found. So alpha is the unknown here. And we can see that alpha is in the k direction. BA, as we calculated right over here, is in the I direction. So K cross product I, this alpha will appear in the Y component equation, or the J unit vector equation. And then AB, the acceleration that it has, this B point's acceleration, is due to the constant angular velocity rotation, and the acceleration of that will be towards the center, towards point O. That means in this graph, let me just raise these parts so to see that clearly, this acceleration of B will be towards the center. This is the acceleration of B, and this is due to the centripetal acceleration, and the resolution of that will be a negative I and a negative J in that sense, resolution of this AB vector in this XY frame. AB vector in the XY frame will have a negative I and a negative J direction. And this is just omega squared R. This is R information. Omega squared R is the centripetal acceleration. And this is about the resolution of this vector in our selected frame. Okay, just take a look at it here. So it's downward direction, and the resolution of this vector is, if this is the x-axis, this is the y-axis, is going to be resolved as a negative x in this direction. Okay, so this is the AB in x direction, and then in the y direction, it's also going to be negative AB y. This is x, this is y. So just to have a larger view of what I have just said, this is it. And then we can combine now the equations here. The first equation was about the relative velocity. We did not really talk about it. There is our acceleration of A with respect to acceleration of C, and this is our rotating frame equation. AC, as it's a fixed point, is equal to 0. CA is basically the same point, A and C, so that's equal to 0. It will also cancel out this part. So we're just going to remain with the Coriolis acceleration. V relative is something that we have solved already, and A relative is something we don't know. But what we know about A relative is that it's going to be in the x direction for sure. We have already found it out around here that V relative is in the I direction. Therefore, A relative should be in the I direction relative to this color. Okay, so it will be in the I direction. But the magnitude of A relative, we don't know. But the good news is that alpha will appear in the J-axis equation, so we don't really need to solve for A relative. If we combine these two equations, there is our A relative information in the I direction and the magnitude is unknown. There is our information of alpha. It is in the j direction. Good news, because we don't need to solve for a relative. Although we could, because we could also work out the x component equation, but it's not really asked in the question. Therefore, we use the y component equation, only the terms in the j-axis. So these are the terms. And if we make use of that, there is our single scalar equation, which we can find out the alpha magnitude for this question.